Hello everyone. We present our work titled Learning Neuro-symbolic Programs for Language-Guided Robot Manipulation. The authors are from IIT Delhi. Our aim here is to learn a function manipulation program parameterized by data that takes in an initial scene and the language instruction as input and outputs a sequence of subgoals for the robot to execute. We assume that the robot has low-level behaviors to perform primitive operations like pick and place. During training, we assume a corpus of human demonstration in the form of an initial scene, an associated language instruction, and the corresponding final scene. The prior work that tackled this problem has one of the following three limitations. They either rely on hand-coded symbols for concepts, or they require dense subgoal supervision in the form of intermediate states, or they don't have object-centric representation that are really required for complex reasoning. Our work overcomes all these three limitations. In particular, we assume a DSL, however, the semantics are learned from data. We don't assume any intermediate subgoal supervision, and our state representation is object-centric. We propose a neurosymbolic approach to this problem. Let me describe the key aspects of our solution. First of all, we postulate a latent space of program composed of object level and spatial concepts. Such a program representation helps us in performing symbolic reasoning over those concepts. We don't assume anything about the semantics of those symbols, and the semantics are learned purely from the data. Moreover, the program representation is compositional, which means that we can perform multi-hop reasoning. This diagram describes the model architecture in detail. The visual extractor extracts an object-centric scene graph from the initial scene. The natural language instruction is fed into the language reasoner and it outputs a symbolic program. The visual reasoner takes in the scene graph and the symbolic program and grounds the symbolic program on the scene graph. The action simulator then takes in the grounded program and outputs the final locations for the object to be manipulated. The loss is taken over the predicted and true final locations of the objects, and the visual and action modules are learned through backpropagation. The language reason is learned through reinforce. This example illustrates the working of our model. The visual extractor extracts the scene graph and the language reasoner extracts the program. The visual reasoner takes in the program and performs a quasi-symbolic execution in a bottom-up manner and grounds the program on the initial scene. The action simulator then takes in the location of the grounded objects and predicts the final locations for the object, and the final locations are fed into the robot and it performs the pick and place operation. We also provide a scene reconstruction module that visualizes the planned rollout before actual execution. The scene reconstruction module takes in the subgoal predicted by the NSRM and visualizes the scene in which the subgoal is actually true. We compare our model with two baselines. First, we modify neural model networks to create a neural-only baseline for our model. In particular, we forgo the latent space of program and the grounding is done through a sequence of attention modules. The results show that our model outperforms the neural-only baseline by a significant margin, and hence the latent space of program really helps us in performing complex reasoning over multi-step instructions. Next, we compare our model with Clipboard, which is the current state of art. Clipboard uses a dense image-based state representation and it predicts a pick and place location through language-guided attention masks. The experiment shows that our model outperforms Clipboard in significant margin, especially in the tasks where predicting the pick and place locations require complex object level and spatial reasoning. This is an illustrative example where our model beats the clipboard. We show that our model has strong generalization abilities over richer scenes and multi-step plans. Consider this example where we trained our model on 2-step instructions and tested it on 5-step instructions. The simulation show that the execution is robust and the prediction is accurate. In conclusion, our model shows strong generalization ability to novel scene and instruction. Moreover, we trained the model end-to-end without any sub-goal supervision, and the experiment shows that our model outperforms clipboard and the neural-only baseline we have created. Future works involve learning higher-order concepts and learning to detect and recover errors that arise during execution. Thank you one and all for listening to this talk.